Good morning. This is Miss Billerbeck, and we're going to talk about analyzing lines of best fit. So, a linear regression is a method used to calculate the line of best fit. Well, that's kind of a scary word, but all it means is that you're going to be looking for a trend line or line of best fit to match your data, the scatter plot. Okay, so that's all linear regression does. So linear regression is a method used to calculate the line of best fit. The line of best fit is the trend line that most closely matches the data. So how is the data trending? What are the trends out there? So who's buying what? That's the trend of the data. Okay, so the correlation coefficient R is the number between -1 and 1. So that's kind of important, -1 and 1. So R can't be anything outside of -1 and 1. It could be 0.9, it could be -0.3, but it can't be 2 or 5 or -3. Okay, it has to be between -1 and 1. So that correlation coefficient indicates the direction and strength of the linear relationship in a bivariate data set. So remember we talked about bivariate before. So bi means two, like bicycle, and variate means variables. So remember, if it's a scary word, take it apart. Two variables, data set. Okay, so that's literally what it means. Okay. So let's take a look at a bivariate data set. Okay, so this is kind of a boring set because it doesn't really say what X and Y are for. Okay, but this is a data set. So we want to find the line of best fit for this data set. Okay, and then when we find that line, it'll give us a correlation coefficient. So I've already used my TI-84 to do this. So what you do for a TI-84, so if you see, let's see if we can see that. So if you go to this key stats, okay, so first you have to go to the key on, okay, and then key stats. Okay, so you'll see in the stats key, it has edit, calc, and test. So first you're going to go to edit. So you're going to see I have already input the data list. So list 1, whoops, you're looking at list 4. Let me get back to list 1. So list 1 and list 2, you can see list 1 and list 2. There we go. Okay, that data is just the data from this table. Okay, so list 1 is this data, and list 2 is this data. So now I'm going to go back and push the stats button, this stats button right here. And instead of edit, I'm going to go to calc. And then I see on calc, I have linear regression right here, number 4. So I can either type 4 or I can go to linear regression. And if you notice, it has AX plus B, like MX plus B on it. So that's kind of nice, like the slope intercept line. In fact, that's what it is. Okay, so you hit enter. And then it asks what list are you pulling your data from. Since I have multiple lists of data, I've put in list 1 and list 2. And the lists, the numbers of the lists are above the keys. So if you look at a TI-84, you'll see in blue list 1, list 2. So if it's not saying list 1, list 2, you just hit second list 1, second list 2. All right, so now I'm going to go down and hit calculate. And look how easy it is. It just gave me the whole equation, and it gave me R. So I was actually going to do this using the online TI-84 that I downloaded, but it didn't give me R. I couldn't believe it. So if we look at this R, it gives us 0.9954. Wow, that's so close to 1. So let's write what they gave us. So we have y equals, and they said a was 13.5. Now I'll round that to 6x plus 17.59. So that's my linear regression. So this is a linear regression of the data. And the calculator gave us an R for this linear regression of 0.9955. So that is so close to 1. So that means that this data, if we plotted it using stats plot, well, it's already, I set it up with stats plot already. So we'll hit this graph button, and you can see that's the data plotted. Aren't graphing calculators wonderful? Okay, so it gave us that data set. So it really does show that it's following a line really well. So that has a strong correlation, a strong positive correlation, actually. So when we look at the correlation coefficient, we can say that is definitely a strong, almost fierce. We can write fiercely. Well, it's a fierce correlation. Actually, we don't use the word fierce. I'm joking. Correlation. But it's a positive. So we mustn't forget about that. So it's positive. I'll put fierce in here because it's not a math term. Should be, definitely should be, positive correlation. There we go. All right. So that's what we get when we have an R that's almost 1. So this, if we rounded it, that's almost 1. So that's what an R of 1 means, that it would fit almost every point is on the line. All right. So let's look at these correlation R's to figure out what are we looking at. Okay, so this R 0.1, I'll draw you a picture of what 0.1 would look like. Where you could kind of say, hey, there's really something going on like that. It's almost a cloud of data, but you could kind of pick something out. Okay, of a negative 0.6, this one would look like this, where probably where you could get a line like that. Okay, so 1 is a little bit more cloudy and farther away. 6, we might have a few out there. Okay, but if this one's a negative correlation versus this one's a positive, 0.1 would be, well, I guess that actually doesn't matter. The slope doesn't matter. It's the spread of the data that matters, okay? So an R of 0.8. So an R of 0.8 is going to be pretty close, and where you know that if you draw that line, most of the data is going to be there. Okay, so let's take a look at the R of 1.2. Oh, wait. Can we have an R of 1.2? You can't have an R of 1.2. Okay, so you can't have it. Okay, it's not between -1 and 1.2. So don't fall for that if I put it on the test, okay? All right, so next I want to talk about residuals. Okay, so a residual is the difference between the y value of a data point and the corresponding y value of the line of best fit. Okay, so when you're out there taking your actual data, hopefully it's very unbiased data, and you're taking your data and you find your line of best fit, the residual is this difference between your actual data and this line of best fit, which is like the average trend of your data, okay, where you might have 2 or maybe 3 points on the line of best fit. So this little black point here is your predicted value on the line of best fit. But this one is the actual value of the line of best fit. So to calculate the residual, you take the actual value minus the predicted value. So sometimes you'll have a positive residual. So this value is much higher than the actual line of best fit. So that'll be a positive residual. So let me write that on there. So positive residual. And this one right here is going to be a negative residual. Okay, so when you look at it, you should be able to see, oh, if it's above the line, it's going to be a positive because it's actual. That's my actual minus the predicted. Okay. All right, let's do this example here. I already put it into my calculator and calculated the line of best fit. And when I went and looked at the table values for this one, so what I did is once I found the line of best fit and I wanted to find the actual values at 0, 1, 2, 3, 4, 5, 6, 7, I was doing something kind of crafty here with my graphing calculator. So you can take the line of best fit. Oh, remember the on button? There you go. Okay, so let's go to y. So the y equation, you can kind of, let's see, there we go. Okay, so you can kind of see what I've written in there. It's the exact y equation that is on this board right here. Okay, so when you put it in the y equals and you hit the table right here on your graphing calculator, so you have to go, instead of graphing, we know it's only graphing that first set of data I had, the stats plot, so you can't just graph that line. Besides, that line it's on here, it's just way off the screen, so it's not showing up. So, but if you want to see the table of values, you go to table. Now I've already preset the table value with table set, so it starts at 1, but I could go to 0 too if I wanted to, and just zip up to 0. So then I put in all the values that I found here on this. Can you see that? There we go. So those are all the values on the graphing calculator for these values here. So I just took it right off the graphing calculator and filled it in versus a graph, because I felt it's easier to calculate the residual more accurately this way. So if we go ahead and we talk about residuals, the actual value versus the predicted value. So this is the actual value of, and let's talk about what we're actually looking at as far as these numbers. So the owner of a flight school collected enrollment data using the line of best fit, find the residuals. Okay, so he's trying to figure out what he should be, how he should be planning his resources to accommodate his regular enrollment. Okay, so this is a useful thing for a business. So when we look at this residual, we have actual minus that. So we're going to have a negative number. So that's going to give us 45, negative 45. All right, so this one is still going to be negative, but negative 6. So they're very close. So the predicted is a little more than that. So 905 minus that, this gives us a positive number. So we end up having 25. 928 minus that gives us a positive. So we have 47. 903 minus that gives us 20. And then this is just 3. And then we have a smaller number here. So we're going to subtract this, and remember it's negative. So that gives us 320, negative 23. And then this is going to be negative 20. And there we have it. So that's how we calculate the residuals. So we just take the actual minus that. So sometimes we're going to have negative residuals, and sometimes we'll have positive residuals. Okay, so so the residuals is just showing you about how far your line of best fit is from the actual data. Okay, it's different than the coefficient correlation coefficient, which is R. Okay. All right. So let's take a look at some definitions here. So interpolation is using a model to estimate the data value within the range of known data. Okay. So if I were to estimate something in here and say, oh, I wonder what the y value is when the x is here, and I find that it's going to be right about there. Okay, so that's called interpolation. Okay, so it's within the range of the known data. So this is considered my known data right here. Okay, extrapolation is using a model to make a prediction about a value outside the range of the known data. So let's say I had this data right here, and I decided, oh, hey, I want to know what it's going to be when x is way over here, but that's way outside my data, or maybe at 0, and that's outside my data. Remember the hawk, and we went and looked at the wingspan compared to the length of the wing at 0, and it had a wingspan when there was no hawk at all. So, and I talked about in data. So in data can be a little dangerous, or data that's way outside the data that you've taken. Like, let's say we predict, how tall a teenager is going to be based off the growth curve of a baby. That would be extrapolation. Okay. But if we want to know how big the baby's going to be at 8 months and predict, the growth rate of a baby using the growth rate curve for a baby, that would be interpolation. Okay. So causation is a very important thing. Okay. So we can use numbers and statistics to pretty much support anything we want to, if we're clever enough. Okay. So causation describes a cause and effect relationship. So we really need to look at the data and see, is there really a cause and effect relationship between the two variables, the bivariate data? So that is causation. It's very important. Okay, so we'll discuss these things in these next 2 slides. All right, so this one we have air miles traveled in thousands, and we have number of years since 1975. Okay, this is pretty classic, number of years since 1975. So this isn't year 10, year 20, year 30. It's 10 years after 1975. So that's 1985. That's 1995. That's 2005. That's 2015. And that's 2025, which obviously there's no data because we're not there yet. Okay? So we want to estimate the number of miles people flew in 2012. Well, let's see what we can do there. Okay, so if we take a line, so we have to figure out, well, what is 2012? So remember we were at 85, 95, 105, 2015. So 2012 is right about there. Okay, so if we go put a little line here. Okay, so there we go. We put something right about here. So that's about 2012. Okay. I'm just, I might not be exact. Okay, so that's 2010, so it's a little closer in there. All right, so we want to figure out, well, what is this going to be? So again, I've already put in the data for this into the graphing calculator, and I got the line y equals 47.87x plus 1345. And by the way, I got an R of 0.98. Is that not awesome? That's so close to 1 that means this data is very linear. And you can kind of see it's very linear here. Okay, so upon inputting 2012, we have to look at, well, how many years since 2000? So you have to actually do 2012 minus 1975. Okay, so that gives you 7. Okay, 3, so 37 years. So that's what you input into here to figure out what is it in 2012. So at 37 years, we get, and this actually, you guys have to remember that this is in thousands. Okay, so if you actually put it into this equation, what you're going to get out is 3,100. Actually, let me not use a comma because we have a comma in the number. So 3,116.23. Okay, so we get that, but this is thousands of miles. So the answer is estimate. So if you didn't use this in your actual estimated, you'd find it be right about here, probably right there. Okay, which would be, a little above 3,000. So the actual number, though, ended up being, because it's thousands, is 3,116,230 miles. Okay, so please don't forget. Okay, that's 3,000. Whoops, that was kind of messy, huh? So don't forget that you're going to multiply by 1,000. Okay, so that's another classic mistake in reading charts is the magnitudes that they put in here. So they don't want to put a bunch of zeros, so they shorten up the numbers. Okay, and that's how they can keep the numbers narrower here. Okay, so anyway, that's how many miles we actually went. So this estimates it pretty well at 3,100,000. Okay, so how reliable is this prediction? That's the important thing. So are we talking about interpolation or extrapolation? So interpolation means it's within the data. So technically we're within the data. Extrapolation would have been in what's going on in 50 years from 1975. We haven't been there yet. So how many would you predict? That's considered extrapolating. Okay. The other thing I want to point out, do you see this little squiggly right here? So it looks like this on the y-axis. It goes like this. Okay, that's really common for statistics. Okay, on a y-axis, that means we're skipping. We're skipping a bunch of data because all the action is happening right here, and we want to represent it in a concise way. Okay, just like when I hit the graph on when I hit the graph button on here, and it only shows the one case that lands in this range, and it's not showing the case that lands, at the hundreds range. That's because I didn't do any kind of skip or reformatting of the screen. So this is a quick way to reformat the screen, okay, is to do a little skip saying, hey, I'm jumping from 0. There's a lot of data in here, and let's start with 14 on this. It's actually 1,400,000, by the way. So we skipped quite a bit of data right there. So that's what that little zigzag symbol is. All right. So we have one more example. So let's talk about this one. We've got a number of cars in a number of cities show a positive correlation to the population of the respective city. Can we infer that an increase of cars in a city leads to an increase in population? So if there are more cars in the city, does that mean there's more people? Or does that mean if there's more people, there's more cars? What's causing what? Okay, so this is an example of causation. Okay, so causation, we want to make sure that is there a causal relationship. Well, okay, but maybe there's one with the number of people producing more cars, but I don't think we can go backwards and say cars are producing people, can we? So more people would need more cars, but cars are not going to be producing more people. So there is no causation in that direction. Okay, so again, we need to be careful in statistics to really think about what is being said and does this make sense? All right. Well, that's it for this chapter, actually. So you have a wonderful day. Bye-bye.